Welcome to a deep dive into two fundamental challenges in machine learning, overfitting and underfitting. Understanding these concepts, along with the bias-variance trade-off, is crucial for building models that generalize well to new, unseen data, which is the ultimate goal of any supervised learning task. In supervised learning, our aim is to train a model on a labeled dataset so it can learn a mapping from input features to output targets. We want this model to perform accurately not just on the data it was trained on, but more importantly, on new, unseen data. This ability is known as generalization. Overfitting occurs when a model learns the training data too well, capturing not only the underlying patterns but also the noise and random fluctuations specific to that dataset. Imagine trying to fit every single data point perfectly. The model becomes overly complex and loses its ability to generalize, essentially memorizing rather than learning. When presented with new data, an overfit model will perform poorly because it's too tailored to its training examples. On the other hand, underfitting happens when a model is too simple to capture the underlying patterns in the training data. It's like trying to explain a complex phenomenon with an overly simplistic rule. An underfit model performs poorly on both the training data and new data because it hasn't learned enough from the available information. It fails to identify the meaningful relationships between the input features and the target variable. These two phenomena are intimately linked through what's known as the bias-variance trade-off. This trade-off is a central concept in understanding model complexity and its impact on performance. Effectively, we're trying to find a sweet spot between a model that's too simple and one that's too complex. Bias refers to the simplifying assumptions made by a model to make the target function easier to learn. High bias models are typically too simple and make strong assumptions about the data, leading to underfitting. They consistently miss the relevant relations between features and output, resulting in a systematic error. Linear regression, for instance, has high bias when modeling nonlinear relationships. Variance, conversely, refers to the model's sensitivity to small fluctuations in the training data. High variance models are typically very complex and tend to overfit. They learn the training data and its noise too precisely, leading to large errors on new data because they're too specific to the training set. Decision trees with deep branches are examples of models that can exhibit high variance. The bias-variance trade-off dictates that as you decrease bias, you usually increase variance, and vice versa. A model with high bias will underfit, showing poor performance. A model with high variance will overfit, also showing poor performance, particularly on unseen data. Our goal is to find a model complexity that minimizes both, leading to the best generalization error. The impact on model performance is profound. A model suffering from high bias will consistently produce predictions that are far from the true values, regardless of the training data. A high-variance model might make very accurate predictions on its training set, but its performance will fluctuate wildly and be unreliable on new data. In real-world scenarios, an overfit model might work perfectly during development but fail catastrophically in production, while an underfit model simply won't be useful at all. To mitigate overfitting, several strategies are employed. Regularization techniques like L1 and L2 regularization penalize overly complex models by adding a penalty term to the loss function, encouraging simpler weights. Cross-validation helps by training and evaluating the model on different subsets of the data, providing a more robust estimate of its performance. Increasing the amount of training data can also help, as a larger dataset makes it harder for the model to simply memorize patterns. Early stopping during iterative training is another effective method. For underfitting, common strategies include increasing model complexity. This could mean using a more powerful algorithm, adding more features to the dataset through feature engineering, or adding polynomial features. Reducing regularization strength if it's too high can also help the model learn more intricate patterns. Essentially, we need to provide the model with enough capacity to learn the underlying relationships in the data. Ultimately, balancing the bias-variance trade-off is about finding the optimal level of model complexity. It's an iterative process often involving careful feature selection, algorithm choice, hyperparameter tuning, and robust evaluation techniques. By understanding overfitting, underfitting, and their relationship with bias and variance, data scientists can build more robust and reliable machine learning models that truly generalize and deliver value in practical applications.